practice of cutting ground conductors short within electrical boxes often stems from misconceptions regarding grounding continuity and circuit configurations. Firstly, it's crucial to understand that not all ground wires within a circuit are necessarily continuous from one box to another. Consider a switch loop, where a white wire might run to the switch and a black wire returns to the light fixture. In such cases, the ground wire in the switch box is typically connected to the metal box itself, and similarly, the ground wire in the light fixture box is also connected to its respective box. However, there isn't always a continuous ground wire running directly from the switch box to the light fixture box through the switch. Secondly, residential wiring often involves using one cable for the main circuit and another cable to switch the light on or off. A single circuit could potentially pass through 5 or more boxes, but there might only be one continuous ground wire that effectively ties all of them together. This configuration can create challenges when attempting to pigtail the ground wires together within a box. The intent behind cutting the ground wires short sometimes arises from a misguided attempt to ensure that the grounds are properly pigtailed to wires originating from the same cable. The concern is that if grounds from different cables are mixed together and an upstream ground connection fails, the entire downstream grounding path could be compromised. By cutting the ground wires short, the installer aims to limit the pigtailing to only those grounds that are on the same cable, theoretically reducing the risk of losing the entire ground connection due to a break in a single wire. However, this approach has significant drawbacks and is generally not permitted by electrical codes. One of the major problems with cutting ground wires short is that it often makes it difficult, if not impossible, to properly pigtail the grounds to the designated grounding screw within a box. Electrical codes typically require that all ground wires within a box be connected together and then connected to the box's grounding screw. Cutting the wires short leaves insufficient length to make these connections securely and reliably. Additionally, cutting the ground wires often interferes with the proper securing of the cable using cable clamps. These clamps are designed to grip the cable sheath, including the ground wire, to provide strain relief and prevent the wires from being pulled out of the box. When the ground wire is cut short, it can be difficult to properly position and tighten the cable clamp, potentially compromising the mechanical integrity of the connection. It's important to emphasize that this practice of cutting ground wires short is generally not allowed by electrical codes. Modern electrical codes prioritize maintaining continuous grounding paths throughout the entire electrical system. The purpose of the grounding system is to provide a low impedance path for fault current to return to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and de-energize the circuit in the event of a ground fault. A broken or discontinuous ground wire can significantly increase the impedance of the grounding path, slowing down the response time of the overcurrent protection devices and increasing the risk of electrical shock or fire. The proper method for grounding electrical boxes and devices involves maintaining continuous ground wires throughout the circuit. This means that the ground wires should run from the service panel to each box, and then continue to the next box, without being cut or interrupted. Within each box, all of the ground wires should be pigtailed together, along with the jumper wire that connects to the box's grounding screw. This ensures that the box is properly grounded, and that the grounding path remains continuous even if one of the ground wires becomes disconnected. When working with metal boxes, it is important to ensure that the box is properly bonded to the grounding system. This can be achieved by using grounding screws, grounding clips, or other approved methods for bonding metal enclosures. The bonding connection should be secure and reliable, and it should be inspected regularly to ensure that it is in good condition. In some cases, it may be necessary to install additional ground wires to ensure that the grounding system is adequate. For example, if the existing ground wire is too small to handle the potential fault current, it may be necessary to install a larger ground wire. It is also important to ensure that the grounding system is properly tested and inspected to verify that it is functioning correctly. Ground fault circuit interrupters, or GFCIs, are an important safety device that can help to protect against electrical shock. GFCIs are designed to detect small imbalances in the current flowing through a circuit and to quickly trip the circuit if a ground fault is detected. GFCIs are typically required in areas where there is a high risk of electrical shock, such as bathrooms, kitchens, and outdoor locations. When installing GFCIs, it is important to follow the manufacturer's instructions carefully and to ensure that the GFCI is properly grounded. The installation of electrical wiring and grounding systems should always be performed by a qualified electrician who is familiar with the applicable electrical codes and standards. Attempting to perform electrical work without the proper training and experience can be dangerous and could result in serious injury or property damage. Electrical codes, such as the National Electrical Code, or NEC, provide detailed requirements for the installation of electrical wiring and grounding systems. These codes are designed to ensure the safety of electrical installations and to prevent electrical hazards. It is important to be familiar with the applicable electrical codes and standards before performing any electrical work. The NEC, for example, specifies requirements for grounding electrode systems in Article 250. Grounding electrode systems often involve a grounding electrode conductor connected to a ground rod, a metal underground water pipe, or a concrete encased electrode. The size of the grounding electrode conductor is determined by NEC Table 250.66 based on the size of the ungrounded conductors. The NEC also addresses equipment grounding in Article 250. Equipment grounding conductors provide a path for fault current to return to the source, and they are typically required for all electrical equipment that is likely to become energized. The size of the equipment grounding conductor is determined by NEC Table 250.122 based on the size of the overcurrent protection device. Furthermore, the NEC covers bonding requirements in Article 250. Bonding involves connecting metal parts together to create a low impedance path for fault current. Bonding is important to prevent voltage differences between metal parts, which could create a shock hazard. The NEC specifies bonding requirements for various types of metal parts, including metal water pipes, metal gas pipes, and metal raceways. The NEC also addresses specific grounding requirements for different types of equipment and systems. For example, the NEC has specific requirements for grounding swimming pools, spas, and hot tubs in Article 680. These requirements are designed to prevent electrical shock hazards associated with these types of installations. Similarly, the NEC has specific grounding requirements for sensitive electronic equipment, such as computers and medical equipment in Article 647. These requirements are designed to protect this equipment from damage due to voltage surges and other electrical disturbances. It's important to know that local jurisdictions may have their own electrical codes and standards that are more stringent than the NEC. Therefore, it is essential to consult with the local electrical inspector or building department to determine the specific requirements that apply to a particular installation. Proper grounding and bonding are essential for ensuring the safety and reliability of electrical systems. By following the applicable electrical codes and standards, and by using qualified electricians, it is possible to minimize the risk of electrical shock, fire, and equipment damage. When troubleshooting grounding problems, it is important to use the correct tools and techniques. A multimeter can be used to measure voltage and resistance, and a ground impedance tester can be used to measure the impedance of the grounding path. It is also important to visually inspect the grounding system for any signs of damage or corrosion. If a grounding problem is detected, it should be corrected immediately. Ignoring a grounding problem can create a serious safety hazard. The principles of grounding and bonding are based on fundamental electrical theory. Understanding these principles can help electricians and other electrical professionals to properly design, install, and maintain electrical systems. One important concept is Ohm's law, which states that the voltage across a conductor is equal to the current flowing through the conductor times the resistance of the conductor. This law can be used to calculate the voltage drop in a grounding conductor, which is important for ensuring that the grounding system is effective. Another important concept is impedance, which is the opposition to the flow of alternating current. Impedance is made up of resistance and reactance. The impedance of a grounding path should be as low as possible to ensure the fault current can flow quickly and safely back to the source. In addition to Ohm's law and impedance, there are other important electrical concepts that are relevant to grounding and bonding. These include capacitance, inductance, and electromagnetic interference, or EMI. Capacitance is the ability of a conductor to store electrical charge. Inductance is the ability of a conductor to oppose changes in current flow. EMI is electrical noise that can interfere with the operation of electronic equipment. A well-designed grounding and bonding system can help to minimize the effects of capacitance, inductance, and EMI. The selection of grounding and bonding materials is also important. Grounding conductors should be made of copper or aluminum, and they should be sized according to the applicable electrical codes. Bonding jumpers should also be made of copper or aluminum, and they should be sized to carry the maximum fault current that could flow through the connection. Grounding electrodes should be made of materials that are resistant to corrosion, such as copper-clad steel or stainless steel. The installation of grounding and bonding systems should be performed in a neat and workmanlike manner. All connections should be tight and secure, and all conductors should be properly supported. The grounding system should be inspected regularly to ensure that it is in good condition. If any problems are found, they should be corrected immediately. Proper grounding and bonding are essential for the safety and reliability of electrical systems. By following the applicable electrical codes and standards, and by using qualified electricians, it is possible to minimize the risk of electrical shock, fire, and equipment damage. Grounding systems in electrical installations serve several crucial purposes. Firstly, they provide a low impedance path for fault currents, enabling overcurrent protection devices to operate effectively and quickly clear faults, minimizing the risk of electrical hazards. Secondly, they help to stabilize voltage levels, reducing the likelihood of voltage surges and transient voltages that can damage sensitive electronic equipment. Thirdly, they minimize electrical noise and interference, improving the performance and reliability of electronic systems. A properly designed and installed grounding system is essential for ensuring the safe and efficient operation of any electrical installation. Several different types of grounding systems are commonly used in electrical installations. One common type is the equipment grounding system, which connects the metal enclosures of electrical equipment to the grounding electrode system. This helps to ensure that the metal enclosures are at ground potential, reducing the risk of electrical shock if a fault occurs. Another common type is the neutral grounding system, which connects the neutral conductor of the electrical system to the grounding electrode system. This helps to stabilize the voltage of the neutral conductor and to provide a low impedance path for fault currents. A third type of grounding system is the isolated ground system, which is used to isolate sensitive electronic equipment from electrical noise and interference. Isolated ground systems use separate grounding conductors that are not connected to the equipment grounding system. The selection of the appropriate type of grounding system depends on the specific requirements of the electrical installation. Factors to consider include the type of equipment being used, the voltage level of the system, and the potential for electrical noise and interference. The grounding electrode system is a critical component of any grounding system. The grounding electrode system provides a connection to the earth, which helps to stabilize voltage levels and to provide a lower impedance path for fault currents. Common types of grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes. The size and number of grounding electrodes required depends on the size of the electrical system and the soil conditions. The grounding electrode conductor connects the grounding electrode system to the electrical system. The size of the grounding electrode conductor is determined by the size of the electrical system. The grounding electrode conductor should be made of copper or aluminum, and it should be protected from physical damage. Bonding is the process of connecting metal parts together to create a low impedance path for fault currents. Bonding is essential for preventing voltage differences between metal parts, which can create a shock hazard. Common types of bonding connections include bonding jumpers, bonding bushings, and bonding locknuts. The size and type of bonding connections required depends on the size of the electrical system and the type of metal parts being connected. Surge protection devices are used to protect electrical equipment from voltage surges and transient voltages. Surge protection devices are typically installed at the service entrance of the electrical system, and they divert surge currents to ground. There are different types of surge protection devices available, including surge arresters, surge suppressors, and transient voltage surge suppressors, or TVSS. The selection of the appropriate type of surge protection device depends on the specific requirements of the electrical installation. Regular inspection and maintenance of grounding systems is essential for ensuring their continued effectiveness. Grounding systems should be inspected for signs of corrosion, damage, and loose connections. Any problems that are found should be corrected immediately. Grounding systems should also be tested periodically to verify that they are functioning correctly. Ground impedance testing can be used to measure the impedance of the grounding path, and ground resistance testing can be used to measure the resistance of the grounding electrode system. In conclusion, the practice of cutting ground wires short is generally not recommended or permitted by electrical codes. It can compromise the safety and effectiveness of the grounding system. Proper grounding techniques should always be followed to ensure the safe and reliable operation of electrical installations.